Hello everyone, welcome to the next talk on the water series by Majumdar. Today's talk will be given by Prognadipto Majumdar, and the topic is what is chromatic graph cohomology. He is broadly interested in algebraic topology and related aspects of mathematics. Over to you.
Hi, good morning everyone. So before we begin the talk, I would like to talk about some ideas of the talk. So two important ideas are categorification and graph invariance. And first of all, let's talk about categorification. So what is categorification? So I'll give you a very vague idea of it. So you have the Betti numbers. So the nth Betti number discounts the vaguely n-dimensional holes in some topological space. So historically speaking, this was discovered far before the homology concept of homology came. So with Betti numbers you can't work too much. But what is the Betti number? This is the dimension of the free part of the nth homology group of the space. Well, this is just for convenience. You should be precise. You can trace it with Q. So that is exactly what you want. So once you define the homology groups, you have some structure in it, and you have some particular category. You can actually work with it. You have the morphisms. So the objects remain the same. Here you don't get any extra information. So the extra information is contained in the morphisms from Hi and Hi minus 1. You have some exact sequence, but nothing with the Betti numbers. So this very idea, someone thought I would apply it to graph coloring. So the idea came from something similar. So there was something called knots. In knots we have the Jones polynomial. So when you categorize this, when you try to categorize the structure, you get something called cohomology. This is history. I am not going to talk anything about this. So this similar idea, this motivated what I am going to talk about today. We want to give some structure to graph coloring, and for graph coloring, we have the very well explained polynomial. The chromatic polynomial, very well known thing. And before that, I will raise a question. Graph invariance, there are a lot of invariants. So, first of all, you might think that graph color. Okay, let me define a coloring first. So, given a finite graph G, so G is G comma E, and we will, for the middle part of the term, N will be the number of edges. So, little bit of different convention. So, coloring, this is a map from a certain group to an A with a group. This is a map from the edge set to A such that no two adjacent vertices. This is from B to A. No two adjacent vertices can have the same color. That's a valid coloring. It's just a map. So this should have some connection to the structure of the graph, and as you know, graph is nothing but just some particular topology. So this is a graph for each of the, you have the vertices as the zero simplices and the edges are the one simplice of the graph. So you might think what is the connection with the topology of the graph, with the coloring properties of the graph. As it turns out, the natural topology, the geometric thing, this is not strong enough to classify the graph colorings. So for instance, this is something, this is same as S1 and this is also same to the loop, right? So what is the chromatic polynomial of this? First of all, what is chromatic polynomial? I think I should know. Chromatic polynomial Yeah.
What is the identification that gives the triangle is the same as S1? So what is the topology that we are putting there? Like what is this natural topology?
Natural topology, you just look at this as some topological space.
Oh, embed it in a suitable RL and
Yeah.
look at it.
You don't even have, for this you don't even have to do anything. This is the one simplest at the edges. But yeah, you are right. So the chromatic polynomial is not immediately obvious that it should has to be a polynomial vector. For n, this is let's think of it as a function given a graph G. This is number of colorings from with n colors. So after no reason why this should be a polynomial. But let's look at this. What is the chromatic polynomial of this loop? This is identically 0. Because whatever n you pick, you can't have a valid coloring because it's a self edge. And for this, so given lambda many colors, the first is equal color in lambda always, the next one in lambda minus 1, and this in lambda minus 2. So the chromatic polynomial of this triangle, this is P3 in my notation, 3 polygon. This is lambda minus 1, lambda minus 3. So lot of more structure. So this topology won't work. So how to prove this is a polynomial? That is the most important point, and that will be the basis of whatever we are going to do later. So let's set up a recurrence. Okay. Well, you mind if I call this P? No. Sorry. So the recurrence is P of very sorry for the change in notation. I would prefer to keep this as P of P of G mod P of lambda. Lambda is any number. This is equal to P of G minus this is P of G mod G plus P of G. So this needs some explanation. So E is any particular edge in your graph, and you have anything here, and this is your graph. Okay. This is something here you don't care about, and this is another. This is G minus E. Given a valid coloring of this is V and W. This is V. This is W. Given a valid coloring of G minus E, these are very clear, right? You collapse the edge, that will give you G mod T, and this is just the delete the edge. We have a coloring here. So if V and W have different colors, that extends to a valid color of G. Here, V and W different, you can extend it to G. And V and W same. This is not a coloring of G, but this is a valid coloring of G mod T. This is the recurrence which you have it. And yeah, the proof is similar. But this is the most important fact because let me give a spoiler. So here is Pg of lambda. This is G minus C of lambda minus G mod T of lambda. Well, very soon we are going to construct some chain sequences Ci of the graph. Ci of the graph. This should be, this will happen to be Ci minus 1 of G mod T. Of G minus. This will be the exact sequence. Spoiler. I have not even defined how to construct the chain sequence. So this is going to be the most important thing. So where the minus sign comes from, it may be a split exact sequence or not, but the dimensions, so again here we have graded dimensions, will come later on. For the time being, assume that I am saying that the dimensions can be polynomials, not just numbers. So from here, this I minus 1, this picks up an extra negative side. There is some minus 1 to the power I playing in the background. So from here, the dimension of this is equal to this plus this, modulo the sign. So from there, this is the categorification of this particular recurrence. And this is nothing magical. We are constructing the homology group so as we want this. So okay. Before that, what's the time? Okay. So I can give you a vague idea of how to prove that this is a polynomial. That's not entirely obvious. Before that, let me work out some example. So, this chromatic polynomial for n vertices, n disjoint units, n many, you get lambda power n. And okay, you don't need too much more of this. Let me just briefly say this is a polynomial. So do you want me to prove this side? That this is a polynomial, or do you want to? I think we can leave it, right? So let's just say this uses the recipe theorem and the third polynomial. So the basic is that you just construct some generalization polynomial for every graph invariant of this sort. That is the most general thing. The two variables x and y, and using the recipe theorem, you just construct something ad hoc, and at the end of the day, you say that this is the chromatic polynomial because it satisfies the same recurrence. So let me see if I have the final expression. Do I have it? Yeah, I have it. So, g of lambda, this is one limit again. So before this I need one general idea. So M is a module, graded module. So the Q dimension, the Q for quantum dimension. So the idea is first given cohomology which has conditions to quantum theory, but here there is no quantum theory. So that's the key. You don't need to worry about a convergence because everything is finite here. So everything is finite. And this has a really nice property which you want. When you apply it to M plus N, first of all, let's come to the cube model for the chromatic homology. I will require here. Okay. The chromatic polynomial of this was lambda minus 1, lambda minus 1. So for convenience, we will put lambda is equal to q plus 1. Why? Well, later on, let's come to that. So this will be our new notation, lambda q plus 1, q minus 1. Each of these will assign some module, some algebra. So which particular algebra? For chromatic graph homology, first of all we will work with this algebra A2. This is nothing but Vx modulo x. Okay, let's see. So first of all, give a total order on the edges. It's immaterial, but we need some order. So if you have the edge, that's 0, otherwise it's 1. So 0 is equal to 0. Just write it down. Then 1 is there. 1 0 0 2 1 0 0 0 0 1 1 0 1 1 0, and this is 1 1 1. Each of the components you assign some m. M is a copy of this algebra. So here m. Here 2 m's are there. So along this is the height. This is the same height. So this is the relation of height increases I. And how you construct your chain sequence? I think I should have some more space. Okay. So here is the 0 is level, C0. Yeah, level. This level you call epsilon. This is epsilon 1 to epsilon number of edges. On the entire top, I will talk about P3 because it's a nice example. P0 is the general. This is C0. So what is C0? This is in tensor. And this is direct sum of M tensor to. Yeah, for each of these, it seems to tensor up and you take the direct sum of each of the boxes. Just take this is just take C1, C2, C3. Okay. So what to do next? So associated to this, you have the q dimension. For m, you have the 2 degrees. 1 is there, x is there. Degree 0, degree 1, and nothing more about that. So for this one, each of them you have 1 plus q. 1 plus q for this, and for this you have 1 plus q. For the tensor product, the q dimension is distributed as product. So for this one, you take 1 plus q whole q. Maybe I should shift to another one. Maybe this was a mistake of logic again. Then in this one. So for this one you have 1 plus q whole q, and for this one it is 3 1 plus q whole square. This is 3 times 1 plus q, and this is just 1 plus q. And let's take the signs in order. This is C1, so minus, plus, minus. So this should give you guys the chromatic polynomial. So let's see if the calculations are right. Otherwise, I have to check my notes. What's this? This cancels. q minus q should not be there, right? Yeah, this was one. So this guy, which is the same as the chromatic polynomial. Now my next thing, why should this be equal? We are not a proof that the chromatic polynomial is generated by this homology. This is not a proof. So the proof will be from here. This will be the proof. Once you show that there is a short exact sequence, then you go down to the q dimensions. You can say that the q dimensions satisfy the same recurrence as the chromatic polynomial, so they must be the same. And this is the recurrence and this is the dimensions. Okay. So good. This same thing has a better description, which we call as the state sum model, and that's easier to explain and talk about. Because how to do the differentials? Yeah, that's another point. The differentials are, so from here you can look any of the places.
Actually, one question. In this case, q dimension is of m direction and is this difference?
Huh?
Q direction of m direction n is q direction of m minus q direction of n?
No. Wait. Direction.
Is it plus or minus?
Oh, sorry, plus.
Yeah, you use plus for the calculation.
Sorry. Thank you. Yeah. And let's say something. The graded order characteristic. This is of some chain sequence. This is it. Minus 1 power I. This should be the same as minus 1 power I. You will see I. So this proof is from basic homological algebra. Same thing you do in algebraic topology. H can be replaced by C here. The totals are each of them won't be the same. So okay. So let's have the differentials here. So what do you do here? So this is m tensor m. Okay. I'm rubbing the 1 plus 2 for the time being. It's not necessary anymore. So this is a copy of m tensor m. And what is this? So this is 1, 2 and 3. And this is m tensor m. Let me call this vertices A, B and C. This is corresponding to A, this is to B and this is to C. And AB is one component, AB and this is C. So the map should be, the multiplication map here, tensor the identity map here. So this is multiplication of 1 to tensor identity. Identity of 3. The same way you can do for the other components. So this map will have a name. The notation is which two you are multiplying. Okay. So D, here there is an increase. So star 0, 0. So whenever there is an increase from 0 to 1, you put a star. In the rest of it you put 0. So this is D 0 star 0. D 0 0 star. Okay. Now we'll do the same thing with the more convenient construction, which is the state sum. Because once you generalize to arbitrary algebra, this approach will do the same thing, but it's difficult to visualize what's exactly happening. So let's have the state sum. Or better, let me say that. as a user, does it look okay? It's fine. So you are doing the same thing, but now each of the components you can color each of them by 1 or x. This is a new idea. And how does the differential go? This is 1 and this is x. Just give me a second. There is some more notation. Yeah, now you have the gradings of I and x. So S is a subset of E. This is the span of S as well. I of n, this is the number of components, and this is the number of x. So here something, there is the differential, and there are maps going from g mod t and g minus t to g. We want to construct the sequence. Yes, okay.
What is J of S? J of S.
G of s. There is no G of s. I think I of s or then I and j.
Yeah, J of S.
J, okay. J is the number of x's. So even something like this. Okay.
Oh.
We talk about C1. So this means number of okay. That's not interesting.
So what is I? I is a vertex.
No, no. I is the number of components. So let me see. Let me show. This is C21 of G. And G is the same graph. This is the basis, so not yes. This is 1 and this is x. X1. This is the basis of C21.
It's a vector space by this basis.
Yeah, if you take the material linear combinations. Now, how do you go from C21 to C? Yeah, okay. Give me a second. C I plus 1. Sorry. Wait, this is not the number of components, this is the number of agents. Yeah. Number of agents. Let's do this first. And this is C11. This is C11. Okay. Now we go to C21. So you just take an edge and connect them. If this is the edge, so what will it be? This will be the unit. And the multiplication is x. And for the suppose for the sake of say, so this was x and this was x, and you want to add an edge. This belongs to C1, 2. And we want to go to C2 of 2. Add any edge here. So x into x will be 0, so this is 0. So the differential here is exactly 0. N that is the number of it is ordered before E, and there are some total order fixed in the beginning. So this is it. And what is AC? SE, this is equal to some two things, and S is represented by the set and the color. This constitutes the our 2 degree. So this is SE and C. Small AC, this is just S union E. Just the value there. And for E, suppose this is the same component of S. Suppose C, okay, not C. Well, whatever. If it is the same component, then the color is just the same. And if it contains the 2 components, this one is A and B, suppose. I am short of notation because C is there, one C. If this is 1 and X, we just connect them, and 1 and X with X. If it's X and X, the connection will be 0, and this entire thing will be 0. So this is our differential, and it goes from C I plus 1. Now we go to the short interest sequence. This is our sequence we want. J, G1, CIJ. So this map you should call alpha and beta. You see alpha, beta. It should be alpha ij and beta ij, but there are chain maps, and you can just prove very easily everything commutes. So I'm just abusing notation and using alpha and beta, and there's a lot of things going on in the background. You can't just able to prove it, but it's easy. But we say what alpha and beta do, and there is the most important thing. Yeah. So you have a coloring of I C of I minus 1 j. So what is that? G minus E. You have some subset of that with I minus 1 aj and jx. You can just extend this by coloring of G. It will have one more edge. E is there, you just extend it, and whatever color E has, and then this vertex that you can color is the same component. So alpha is the most obvious one, nothing is there. And for beta, so let S equals to this thing belongs here. If E is not in S, you just extend S. Beta is equal to S. They are the same thing. If beta belongs to S, then you just set to 0. Here the color is the same color. This is 0. And it turns out that with this match, this is a short exact sequence. The proof is drudgery, so I won't prove it here. You can just take out your pen and paper and try that. So what I will do is that it gives a long exact sequence of homology. That's the most important thing while calculating our graph homology. So there you have the connecting homomorphism that comes from the snake lemma. And like the explicit form of that, that's easy but very important. Beta star. And we want expression of gamma star, and alpha and beta they are the same thing. So if B belongs to Cij of G minus C. So this bit, suppose it is represented by summation nk sk ck. This represents something in the homology. We want the expressions here for convenience. So gammas are weak. Minus 1 for r. Summation of nk sk union e modulo So what is this? We just add an edge, take the color in, and then quotient out by the edge. So in particular, if this is something here, C and D, this is not the same thing as this because if it's x here and if it's x here, in the moment you add the edge and adjust the coloring, it's 0. And once the quotient is by, it's still 0. So this log x principle, this will help us to calculate most of the things. And here we have some interesting properties which are kind of expected anyway. So for homology, it's easier to prove that so this just goes to the Majumdar formula. Just another thing, the Poincare polynomial. So R of GP, define it. Summation of e power I to the hi. So this is associated with the hi double g, and this will satisfy the Coulomb formula. So from here you can say that R of G1 disjoint union G2 P comma Q is R of G1 in Q R of G2 and at P equal to -1 you get the chromatic polynomial. So the chromatic polynomial is satisfies the multiplicity property as it should. So this is something expensive. Last of all, another question. So, this graph homology, and there's a theorem that over Q, the graph homology will give you no more information than the chromatic polynomial. Which is completely remarkable. And that's kind of obvious because we have the ranks and that's all.
What is this Q?
Huh?
What is this Q? Rational.
Yeah, rational. I mean, I should not be saying this because it's entirely obvious. Once you put the torsion, you have chosen the ranks of the groups to be such that it should match with the chromatic. We have no more information, but what about our arbitrary groups, arbitrary rings and independent rings? There is a lot of them. So, is it stronger? What do we mean by stronger is that can you have two different graphs with the same chromatic polynomial but different homologies? So the answer is yes, it is stronger, but not with this differential. Well, I don't know the answer for this differential over arbitrary algebras such as Px mod etc. I don't know the answer, and I have also not found too much literature of that. But the answer is yes, and it's a simple trivial thing. So we introduce the twist. Very fancy term and a very trivial thing. So a twist is that's a homomorphism of this module. This whenever you take the differential, it's just composing with f. If f is just a map from m to n, nothing more. So yeah, and you should have the f of x, y. This f of x, f of y, because you need the multiplication properties here and you're connecting it when you multiply, that's it. So for the most trivial cases, we can take f to be 0. That's not interesting. you are just what you are saying is that you are taking the zero differential. There's no fun about that, but it gives us something. So the chromatic polynomial of anything with a loop that is zero, because you cannot color it properly because this vertex is connected to itself. And in our chromatic homology, in our normal, in this differential thing, is this zero? So yes, it is zero. So why is that? Yeah, before that, let's see. That answer to is zero. So f is zero for this and this. But obviously this to have different Cij's, and Hi will be equal to Ci with a zero differential. Then another one example, small one. Yeah. So G1 is this. G2 is this. So again, the chromatic polynomials are the same. You can calculate this. I am not calculating the exact values. So for G1, C4, which is the same as H4, that will be Z7. This is, I mean, the shifted by degree 2, and this is just 3. Here they are different, so we have found a stronger thing, but this is not interesting. There is some value differential, something other than zero, and I have not found anything interesting about that. Maybe it's fun to discover, but just there. And so we need to wrap it up within how much time more? How much more time do you have? We have 5 or 10 minutes. We'll take 5 or 10 minutes more. Yeah, I've got 3. Okay. So this result you can prove easily. If you have an isolated vertex, this is the same as Hi of G. This will be G plus G. So what we have when you have a pendant edge? This is G, and this is the pendant edge. So HIG will be equal to HI of G mod E. Shifted by dimension 1. Because of the long inverse sequence, G minus E will be, this will be, okay, this will be G minus E equals to G mod E. This just unit 1 different records. Then I have the long inverse sequence. So this will directly give us the result for trees. So that is kind of bad actually, because this will say that all trees have the same chromatic homology, whatever model, whatever algebra you choose. Because for tree, there is something a BFS, built first search, that exists. So from level 1 you go down, there is something here. And using this fact to say that a tree can be made by adding pendant edges one by one. Take the last part edges here, so each of them is a pendant edge. So n minus 1 edges. And for one of them, this is Z1. Wait, just give me a second. I think Z plus Z1, I guess. Now you have n minus 1 edges. So Z1 plus Z2. After adding n minus 1 edges, your answer will be this. The n minus 1 plus Zn equal to 8, 0 and hi equal to 0 for all I given. With invert. So this says that all will be the same result. So this is not a very strong criteria, but anyway it works. So the chromatic homology works, but there is nothing stronger than this. There is another model, this is the same model, another big result that someone calculates something on the night move. I'm not going to talk about the night move because that requires another lecture. Basically, what is trying to prove is that you have the i's and j's here. I and j. So the non-trivial homologies will cohomology will occur only in the two diagonals. I plus j is equal to 1 in n and I plus j is equal to n minus 1. So the only non-trivial homology. And the torsion thing, non-trivial homology. A non-trivial torsion will happen only if the I plus j equal to n. If I am not sure it was n, it is the figure. The diagram which I drew at first, it was meant to be an example of this, but there was some lack of space. Terminal benzene ring P6 6J I we'll take 5 minutes more, okay? So unfortunately here it is the number of vertices in that result. Then again change of rotation. So this is our result for P6, just an example. This happens for every graph. These two columns will have the non-trivial stuff. And you can forget everything else. And the way to prove the night move, I mean, they consider another differential called phi, and which acts on the homology groups. There is a 2-step forward and 1 step back, right? I think this way. That's why it's called the night move. So this way we will have an isomorphic pairs. So we're not going to speak about that, and we're going to wrap up the lecture now. But before that, there is a question. So we were talking about categorification in the very beginning, right? So what happened with weighting numbers was that you constructed some nice homology groups of some topological spaces and you assigned some abelian groups. That's a very good category. Now what category are we working in this case? So we want something like category of graphs. So here is a graph G and G minus E, you have some morphism between them. G mod E, you have some morphism between them. So this should be the morphism. Now the question is, given any two graphs, G1 and G2, suppose they are linked by some series of operations like G mod E, G minus E, something like that. And suppose there is another step by which you can go to G1 to G2. This will give some morphisms like some combination of alpha, beta and gamma, which right now I don't know. So the question is, if this is a proper category, when you go to the homology, these two morphisms should be the same. The funny thing is that the answer is open. This question is open. So no one knows as of it. So this is where I would like to stop. This is the question. No one knows. So but before I stop, I will give the references. And any questions, anyone? So I think this is what I have to say.
So you told for trees, this thing won't characterize the tree, right? So
No.
for any tree, it's sort of
Yeah.
the same. But is there any class of graphs for which it, like, say, cyclic graphs or something, for which this characterizes?
Characterizes.
I mean, cyclic graphs is there is only one cyclic graph on.
No, cycles are very important because there is a result that when you are working with the algebra AM, I think as far as I remember, for AM you need some cycle greater than M to have a torsion in the mth group, something like that. This is the torsion groups, and the torsion groups are what will help us to classify, because the ranks anyways we have with the chromatic polynomial. We are not going to get anything new out of that. But the torsions are the most fun thing, and there is no clear idea what these torsions mean. The geometrical meaning of that is not well understood. So just give me a second to find out the author's name. Yeah. So these two papers are the categorification of chromatic polynomial and the number 2. This is the cohomology for arbitrary algebras. So these are the same authors. I won't make the mistake of saying the author's name here, but you just read it down, it's not a name. This is the name, you just search it. These are the most important papers for the talk, and two more. Then there is torsion graphomology. Authors are the same person. With some third person, Joseph. In particular, number 2 and number 4 are particularly interesting, and would be nice to read after this one. Michael. The last one, it's not a paper. So if you want to learn more about chromatic polynomial and those stuff, this is a very good book in combinatorics. You can read it from anywhere else, but I found it nice. GPM book. Course enumeration. So this is it. So I will do it. Thank you everyone. Any questions? Okay, thanks.
Does anybody have any questions? Okay, if not, let's thank the speaker once again.